Hello. Consider the following matrix. Matrix A, whose entries are given as follows. The first row has 1, minus 2, minus 2. Sorry, that's 2, the third entry there. The second row has minus 2, 1 and minus 2. And the third row has 2, 2 and 1. What we want to do with this matrix is, for a given vectors, more precisely for a given sequence of vectors, we want to determine for each vector in the sequence whether that vector is an eigenvector of the matrix or not, and if it is, for which eigenvalue this is so. The sequence of vectors to be checked will be the following. K1 is the column vector consisting of entries 0, 1, and 1. K2 is the column vector consisting of entries 4, minus 4, and 0. And K3 is the column vector consisting of entries minus 1, 1, and 1. Before doing the computations, let us step back a little bit and remind ourselves the definition of what is an eigenvector, what is an eigenvalue, and perhaps we can also spend a little bit of time reflecting on the given matrix and the given vectors, perhaps by the Oops, my apologies, I lost my line of thought there for a moment. So what I wanted to say is that we recall the definition of eigenvector and eigenvalue, and then we're going to see if we can make some general observations by just looking at the matrices and the vectors before we set out on the computations required to answer the question. A vector K is an eigenvector for a matrix A when A times K is equal to lambda times K for some scalar lambda. So when this happens, lambda is called an eigenvalue of the matrix A, and K, if it is not a zero vector, is called the eigenvector corresponding to the eigenvalue lambda of the same matrix. Okay. The question we want to look at in this example is whether the vectors that we are given there, K1, K2, K3, whether they are eigenvectors for the matrix A, and if so, for which eigenvalues are they eigenvectors? So basically what we want to do is to check whether we can find eigenvalues fulfilling the required eigenvalue equation. I'm referring here to this equation. So we want to see if this equation can be fulfilled for each of the k's given there for certain values of lambda. Note that if there is such a value of lambda that fulfills the equation for a given k, then that lambda will be unique, because we want ak to be equal to lambda k, and so if you have two different lambdas making lambda k, let's say lambda 1k and lambda 2k, both equal to ak, since ak will not be a zero vector, since k is not allowed to be a zero vector, lambda k being equal to lambda 1k being equal to lambda 2k gives that lambda 1 and lambda 2 are equal to each other. So the lambda that we will find for each of the vectors, if we can find them, will be unique value. But the whole task now is to see if we can find such lambda or not. So what we want is to know whether there is a lambda 1 such that a times k1 is equal to lambda 1 k1, whether there is a lambda 2 such that a times k2 is equal to lambda 2 times k2, and whether there is a lambda 3 such that a times k3 is equal to lambda 3 times k3. If such lambda exists in each case, then it turns out that the corresponding vector is an eigenvector, and then that lambda will be the eigenvalue for which the vector is an eigenvector. But if such lambda does not exist for a given k, then it turns out that that a given vector is not an eigenvector of the matrix. Great. So now that we have reflected a bit on the concepts involved in the question that we want to address, let us see if we can make some general remarks before beginning with the computation specific to the matrices that we are given. For example, one remark that we can make is that a zero vector can never be an eigenvector, but we see here that none of k1, k2, or k3 are zero vectors. There is a zero entry in k1 over here, but that doesn't make k1 into a zero vector. A zero vector is the one that has all the entries zero. So all three vectors that we're given are legitimate vectors as candidates for being an eigenvector. Another thing we can notice is that none of the vectors appears to be a scalar multiple of the other. Like, for instance, k2 isn't a scalar multiple of k1, neither is k3 scalar multiple of k2, and so on. What would have happened if one of them was a scalar multiple of the other? Well, the thing is that if a vector is an eigenvector, then its scalar multiple will also be an eigenvector for the same eigenvalue, actually. And so, unfortunately, we cannot make use of this fact because none of them are scalar multiples of the other. And if they were, then we would only have to check that one of them is an eigenvector, and then we can conclude for free that the other one would have also been an eigenvector. Well, it is also true that if two vectors are eigenvectors, then they're for the same eigenvalue, then their linear combination will still be an eigenvector for the same eigenvalue. But we will not really start investigating now whether one of the k's is a linear combination of the other two, because at this point we don't even know if they're eigenvectors for the same eigenvalue or not. So and also it is not so easy to notice immediately if the linear combination is taking place. So the best thing at this point is to start with the computations. However, if we look at the matrix A, one thing that perhaps we could remark about it is that the matrix A is symmetric. And that means that if you reflect it along the diagonal, you get back the same matrix. There are some wonderful facts about the eigenvectors and eigenvalues of symmetric matrices that could be made use of, but not at this point. That part of the theory is not intended to be used for the purposes of this specific example. Great. So what we do now is to engage in the necessary computations to answer the question. What would these computations be? Well, let's look at one specific equation we're interested in. So let's take the first one with the k1 there. So what we want to do is to figure out whether there is a lambda 1 that makes this equation hold. How are we going to figure that out? Well, one of the obvious things we could do, I guess, is to compute a k1, because we are given a and k, we're also given k1, so we can just multiply these two to get the value for a k1 as a column vector, and then compare that to the right-hand side. The right-hand side is actually a scalar multiple of k1, right? The scalar by which it is a multiple is lambda 1. So all we need with the first equality is that ak1 is a scalar multiple of k1. So we will compute ak1 and I'll see whether or not ak1 is a scalar multiple of k1. And the same goes for the other two equalities as well. So that's the computation we want to do. We want to take the matrix A and multiply the matrix A with k1, and then with k2, and then with k3, and then in each case compare that with the original vectors to see whether the answers are scalar multiples of the original vectors. Great. So let us begin with the first one, and to do that I'm going to move to the next slide by first copying the vectors involved there. There we go. So we have here A and K1, and we want to figure out if there is a lambda 1 that fulfills this equality here. And so for that, as we already said, we're going to multiply A and K1. So what is the product of A and K1? For the sake of clarity, let us do the multiplication of matrices in a bit more detail than we will do in the other two cases. So if the matrix A is that and the matrix K1 is this, then the way the matrix multiplication works, as you probably know already, we take the rows and we multiply it by the column, term by term, and then adding the terms, and that will be the first entry, and then we do the same thing for the second entry and the third entry of the column matrix we're expected to get here. Okay, so the first entry then is going to be 1 times 0 plus minus 2 times 1 plus 2 times 1, and the second entry is going to be minus 2 times 0 plus 1 times 1 plus minus 2 times 1. And the third entry is going to be 2 times 0 plus 2 times 1 plus 1 times 1. Okay, that evaluates to, so we've got here 1 times 0, so that term goes away because 0 doesn't affect the sum. Maybe we can also get rid of all the other terms where there is a 0. And so in the first entry of the resulting column matrix, we have column vector rather, we have minus 2 plus 2, and minus 2 plus 2 is of course 0. And in the second entry we have 1 plus minus 2, and that's minus 1. And in the third entry we have 2 plus 1, and that's 3. Now the question is this equal to some lambda 1 times k1? In other words, is that vector 0, minus 1, 3 a scalar multiple of the vector 0, 1, 1? So let's try to answer this question over here. We want this to be equal to lambda times k1, lambda 1 times k1, which is 0. Of course, we multiply a column vector by a scalar by multiplying in the scalar, and so multiplying each term of the column vector with a scalar. So we'll have here lambda 1 times 1, which is lambda 1, and also lambda 1 here. And the question is whether this equality holds. And of course, we see that for this equality to hold, we will have to have lambda 1 equals minus 1, and at the same time, lambda 1 equals to 3. But that's impossible. The same real number lambda cannot be equal to minus 1 and 3 at the same time, just because minus 1 and 3 are not equal to each other. So the conclusion is that such lambda 1 cannot be found. In other words, k1 it is not an eigenvector of the matrix A. If it was an eigenvector, we should have been able to find a lambda, and we can see here that it is impossible to find such lambda. Therefore, k1 is not an eigenvector. Great. Let us now move to the next vector, k2, and to do that, we're going to copy that one out. I'm actually going to copy the whole thing here and then erase the unnecessary part. And we move to the next slide. Okay, so let's get rid of what we don't want here. We do not want this part, and maybe I'm not going to waste your time for that. Let me pause the video. There we go. So now we only have the things we need to have. We're going to work on the two vectors k2 and k3 both on this slide. So as before, what we want to do is to compute the value for AK2 and then compare that to K2. So the matrix A multiplied by K2 is equal to. Let us not write out the matrix and the vector separately this time. Let us just multiply them through what we've already have written here. So it's going to be 1 times 4 plus minus 2 times minus 4 plus 2 times 0. That's the first entry. And then the second entry is minus 2 times 4 plus 1 times minus 4. Maybe I should make use of some brackets here so that it's less confusing. And then plus minus 2 times 0. And then the last entry is 2 times 4 plus 2 times minus 4. I hope I'm not making a mistake somewhere here. Plus 1 times 0. And this evaluates 2. Okay, so again we get rid of the 0 terms. And then what we are left with is 4 plus 8. And that's 12. So on the next line we have minus 8 minus 4, and that's minus 12. And the last line gives us 8 minus 8, which is 0. Is this a scalar multiple of K2? Clearly it is, with lambda 2 being equal to 3. If we multiply in 3 in the right hand side vector here, we're going to get exactly the left hand side vector. So K2 turns out to be an eigenvector, and the eigenvalue is 3 for that eigenvector. Let us now look at the third one. I committed to be able to fit that on the slide. Let's see if I can do that. Okay, so we'll have, maybe we can just write out the result of the calculation without writing out the long sums anymore. So minus 1 times, 1 times minus 1, that's minus 1, plus minus 2, that's minus 3, plus 2, that's minus 1, right? Then minus 2 times minus 1, that's 2, plus 1 times 1, that's 3, plus minus 2 times 1, that's minus 2, that's 1. And then in the end we have 2 times minus 1, that's minus 2, plus 2, that's 0, and then 1. Is this a scalar multiple of the given vector? Can we find a lambda 3 so that this vector is equal to minus 1, lambda 3 times minus 1, 1, 1 vector? Well, of course we can, with lambda 3 being equal to 1. So then it turns out that K3 is also an eigenvalue, an eigenvector, and the eigenvalue for that eigenvector is, more precisely, it's the other way around. So this is an eigenvector for the eigenvalue being 1. We do not know at this point whether matrix A has other eigenvalues or not. What we do know is that it certainly has 1 and 3 as eigenvalues. It could have more than these two eigenvalues, but that we do not know. We also do not know which other eigenvectors it has. The only thing we do know is that applying the general effect I mentioned earlier is that a scalar multiple of either k2 or k3 will still be an eigenvector, each one for the same corresponding eigenvalue. But that wasn't the task for us to figure out all the eigenvalues and eigenvectors of A. What we wanted to do is just when we are given an eigenvector to know how we could most effectively check whether the given vector is an eigenvector or not, and if it is, for which eigenvalue it is an eigenvector, which we have successfully completed for the matrix A that we were working with. Thank you.